Hello everyone, welcome to the talk on distributed constructions of dual failure fault-tolerant distance preservers. I'm Mirav. Okay, so distance preservers are sparse subgraphs that preserve distance information from the original graph. For example, assume that we are given just a single source and our goal is to preserve distances only with respect to this source. We don't need to keep the entire graph. We can just compute a shortest path tree with n-1 edges, and that contains all the information that we need about the exact distances from the source. The limitation of shortest path trees is that they are very sensitive to faults. So now if a single edge in this BFS tree fails, not only that the structure that we computed is now meaningless, it breaks the graph into several components, and it no longer says anything about the distances between S and the other nodes in the surviving graph. For example, if we just add this edge between V1 and V3, maybe our situation would be better. So our goal in the fault-tolerant setting is to augment the standard distance preservers with additional edges, but not too many, so that they will still maintain distances under faults. Okay, so fault-tolerant distance preservers are sparse subgraphs that preserve distances under either edge or vertex faults, but in this talk we are going to restrict attention only to edge faults. Okay, so in particular we are going to consider the notion of source-wise fault-tolerant preservers. And the definition of these preservers is as follows. Given a graph, unweighted graph G, and a set of sources S, the preserver is a subgraph that satisfies the following. If we look at the distance between S and T in H minus the fault, it's exactly the same as the distance between S and T and G minus the fault, and this should hold for every pair ST in S cross V and for every edge E. In other words, it is required that the preserver H will contain not only a BFS tree with respect to every source, but rather a BFS tree at every graph G minus E with respect to each source. Okay, so and of course, we can always take the entire graph as our preserver, but we really care about the sparsity of these preservers. We would like these preservers to be as sparse as possible. In the same manner, we can also allow some slack in the distances. In fault-tolerant additive spanners, we would like to compute a sparse subgraphs that preserve the distances under faults up to some small additive stretch. In particular, a NEF-T additive spanner is given for a given unweighted graph is a subgraph that satisfies the following for every pair of nodes, S and T. If we look at their distance in H minus the fault, is at most their distance in G minus the fault plus beta. And this should hold for every pair S and T and for every edge E that fails. So both these definitions, as I stated them, is for single fault for simplicity, but of course you can extend it to any number of faults. Also note that in this definition, we always compare ourselves, we compare the distance ST in H minus E to the distance in ST G minus E. So if it happens that the edge E disconnects S and T in G, clearly it's going to disconnect S and T in H, and there is nothing to do. So really the requirement is that if there is a sum path between S and T in G minus E, we should have in our structure H minus E some approximation of that path as well. Okay. So in this paper, our goal is to provide distributed constructions of fault-tolerant preservers and fault-tolerant additive spanners. In particular, we should compute multiple BFS trees or multiple additive spanners in many graphs, G minus E for every edge E that might fail. Okay, so this whole notion of fault-tolerant preservers and spanners, they have been heavily studied in the literature over the 5-10 years, but still little is known about their distributed constructions. Throughout, we will consider the standard message passing model, the congest model, where in this model we can exchange log and bits of information on each edge of the graph. And usually in the congest model, the thing that we care about is the number of rounds, okay? But in our setting, we care about two measures, the number of rounds and the sparsity of the output subgraph. Clearly, if we just allow to take the entire graph, say quadratic many edges, then in 0 rounds we are done, okay? Or if we allow to collect the entire graph, we can just apply the centralized construction and compute a very sparse fault-tolerant preservers. Our goal is to have efficient algorithm, and efficient, roughly speaking, it means sublinear, and algorithm whose output is going to be sparse. And by sparse, I mean subquadratic. That would be our range of interest. Okay. So our results can be summarized as follow. Our first result, which is the starting point for the other result as well, is efficient construction of fault-tolerant source-wise preservers under single fault. And this extends our previous construction with the work with more than a few years ago for a single source. I'll mention that next. We then extend this construction for one fault into a construction of two faults, but still fault-tolerant source-wise preservers. And finally, once you have preservers, you can tweak them into fault-tolerant additive spanners as well. So the main key results is the construction of the preservers themselves. Okay, so I'll start by mentioning the first result. For a given unweighted undirected graph G of diameter D, and a subset of sources S, we can compute this fault-tolerant source-wise preserver with this many rounds, which is sublinear provided that the diameter is sublinear and that the number of sources is sublinear. And the sparsity of the structure is this, which is square root Sn to the 3/2. And this sparsity was shown to be nearly optimal by a previous work with David Peleg. So we provide perfect sparsity, but in sublinear number of rounds. Prior work with Mosen considered a single source case, and for that we provided an OD round algorithm. If you just extend it into multiple sources, you get this multiplicative dependency, okay, which might provide superlinear dependency for a large number of sources. And alternatively, we provide this bound, which is preferable for large number of sources. Okay. In the second result, we actually consider the dual failure case, which is considerably more involved. Also in the centralized setting, dual failure, there is a jump from one fault to two faults. It's not a very smooth transition. Here we provide a subgraph, a preserver with this number of edges. Again, it is subquadratic provided that the number of sources is sublinear. And this is the number of rounds. As I'm going to mention at the end of the talk, this is far from optimal, but at least this is the first result that we have for handling two faults. And as I said before, once we have preservers for multiple sources, we can also tweak them into providing fault-tolerant additive spanners with additive stretch 2, and this is the sparsity that we get, which is again subquadratic with sublinear number of rounds. Okay, so what is the challenge? The challenge, let's just think about the preserver task, a fault-tolerant preserver with respect to multiple sources. As we say, the output structure is a union of many BFS trees. It's a BFS tree of S in G minus E for every edge E that might fail. So in the work with David Peleg, we showed that if you just compute these BFS trees by breaking ties, shortest path tries in an arbitrary manner, the size of this structure is actually small. Small in the sense that it's nearly optimal. It's the right bound. So the only question is how can we simultaneously compute this many BFS trees in a distributed setting? If we just compute a single BFS tree, it takes d many rounds, but we pass a message along every edge in the graph. So if we build this many trees, we will need to send this many messages, and this would lead to a superlinear number of rounds. And the question is, how can we do better? And this question was already partially answered by our previous work for the single source, single fault setting. Okay, so here is our starting observation from the SPA16 paper. The starting observation, if we just consider a single source and a single fault, okay, and we know that we need to compute n many BFS trees with respect to S in every graph G minus E for every edge E in the BFS tree of S. And now we look at from the viewpoint of a node V, okay? And we ask how many of these BFS trees should V be really actively participated in? That is, for a given edge UV, we claim that it's not really necessary to send the BFS tokens of all these n BFS trees, but rather of much fewer trees. And here is the reason. If the failing edge E does not appear on the shortest path between S and V, then the distance between S and V is exactly the same, the path is exactly the same. So there is no reason for you to send information to V about a BFS construction in G minus E because the path remains as the same, okay? However, for every edge E that actually appears on the shortest path from S to V, these are the only important edges for which our target V should learn is new distance, okay? So for every edge UV, it is sufficient to propagate the BFS tokens only from D many trees corresponding to the at most D edges on the shortest path from S to V. So the total congestion is actually D. And now we actually need to solve a scheduling problem. We have n many BFS trees that we would like to compute. We know that on every edge we should send only D many messages, and a single BFS tree can be computed in order D many rounds. So we use the random delay approach, which roughly in this setting what it says is to pick a random starting time for every BFS tree to be some random point in the range, in this range, where D is actually the congestion bound, okay? And I'm omitting many details, so really this is the high-level idea. Start every BFS tree at some random time, and because we pick this range, and because every edge should only pass D many BFS tokens, one can schedule all these BFS trees in congestion plus dilation time, which sums up into D. Okay. So now when considering multiple sources, I would like to break this bound, this S times D barrier, okay? However, if you look again into the structure and you apply the same argument that we just had before for the single source setting, you can see that there might be the case that the node V is actually interested in learning the distances with respect to S times D many edges. That is, for every edge E that appears on the shortest path from Si to V, it is required for V to learn the new distance because all these edges on these shortest paths are actually important. And we have SD many edges, and it looks like it is crucial for V to participate in SD many BFS trees, okay? But we are going to claim that actually it is not necessary and we can do better. And to get an understanding into this improvement, we need to actually look at the most useful and basic concept in fault-tolerant distance preserving setting. And this is the notion of replacement path. A replacement path is kind of the analog of shortest path to the faulty setting, and it has three parameters: the source, S, the target, T, and the failing edge, E. So this is the shortest path between S and T in G minus E. So before we said that the output structure should be the union of all BFS trees at source node S for every S in the set, and in G minus E for every edge E that fails. Alternatively, we can say that this output structure should contain a shortest path, a replacement path PSTE for every ST and E. Also, one can observe, and it has been done in many of the prior work, that it's sufficient to add just the last edge with respect to each of the paths. So if you just take the last edge of each replacement path in this list, eventually you get a preserver, okay? And this will be our goal. Also, one thing that we are going to relax compared to the work with Mosen for single source is that here we are not going to insist on computing the fault-tolerant distances, okay? We just want to compute the fault-tolerant preserver. So at the end, the vertex T might not know its distance in S with respect to each of the faults, but eventually we will just compute the subgraph, okay? So in this relaxed problem, we can, which is the original problem, we can do better. Okay, let me also provide you a structural view of the replacement path, which looks as follows. If this is in gray, you see the BFS tree with respect to S, okay? And in black, you see the shortest path between S and T, and this is the failing edge E. When E fails, it breaks the BFS tree into two parts, okay? And the PSTE path has the following structure. It starts from S, it follows some tree path up to some point where it leaves the BFS tree, and we add some link edge to the first node Y that lies in the subtree that is sensitive to the failing of the edge E. Okay. So this is the structure. We'll come back to that structure later on. So our high-level idea to compute this subgraph efficiently is to distinguish between far and near faults. So we zoom into a source node S and a target vertex T, and we have set some parameter sigma, which is roughly square root n over S, the number of sources. And I said that an edge E is near a fault for T if it lies in this sigma length suffix of the shortest path. So this is the near part. Note that because we have S many sources, if you multiply this by S, you get that every vertex has at most this many near edges, okay? And now our strategy is to have two procedures for adding the last edge of the PSTE path for every ST and E. But these two procedures will depend whether or not the edge E is near T or far T. So here is the ILevel description. The first step of the algorithm is going to sample a random set of roughly square root Sn many nodes, and we will add a BFS trees with respect to all these nodes. The second part will compute all this collection of BFS trees that we want. So it's Sn many trees, but these trees will be truncated, okay? We will filter out some of the messages to keep the congestion bound small, okay? In particular, we are only going to propagate tokens for near faults. So if in the single source solution we propagate tokens for all edges that lie on the shortest path, now we will propagate only tokens whose edges lie in the near part of the shortest path. More specifically, to handle the near faults, this is what we do. We slightly increase the threshold of sigma to 2 sigma. And we let every node to learn this 2 sigma, the last 2 sigma edges of its shortest path, SIV for every SI. Okay. Overall, the number of these edges is good, is square root Sn. Now we let all my neighbors learn my near edges. These are the edges that are important to me. These are the edges that I want to learn about their BFS tokens. So I let my neighbors know, hey, these are the tokens that I care about, okay? So all this can be done in D plus square root Sn rounds. And now we use the random delay approach, and we start each algorithm BFS rooted at S G minus E for every S and for every E in this random time, where square root NS is again our congestion bound. This is the total number of near edges for a given vertex, okay? And for every edge UV, we are going to pass a BFS token in G minus E only if this edge is near V. Only if it lies in this 2 sigma. So I'm taking 2 sigma and not sigma for a technical reason that we'll see later. So only if this holds, then I'm propagated the token, and then we are in a situation where the congestion is really bounded, okay? So I'm omitting many technical details. For example, when I'm saying that I'm passing a token only if it's important for my neighbor, only if this edge lies close to my neighbor, it's also important to send this token at the right time, right? BFS algorithm is only about the time, and I would like to send this BFS token in the round, which is the starting point of the algorithm, which is TSE, that was chosen uniformly at random in this range, plus the distance, okay? So I really want the BFS algorithm, each of the BFS algorithm, to propagate in a round by round manner so that the construction will be correct, okay? But I will pass these tokens only if they lie in the near segment. So this is the very high level idea of the algorithm. I'll just give some hints about the round complexity and the correctness. So the computation of the random trees can be done in this many rounds just by using the random delay approach. So handling the far faults is cheap. Then we are going to compute this many truncated BFS trees, but since we only propagate edges of near edges, the total congestion is going to be this square root Sn, and using the random delay approach, this can be done in, again, square root Sn plus the remaining rounds. Now let's look at the correctness analysis and first consider the case where the failing edge is far, is not in the last sigma suffix. So we are back to consider only the sigma length suffix, okay? So if the edge E is far, it also means that the replacement path must be long. The length must be at least sigma, okay? So now we look at the last sigma over 2 suffix of the path, and we claim that with high probability, one of the nodes that we sampled into R must lie in this suffix, okay? So we have a sampled node R, a distance at most sigma over 2 from T, and because the edge E is far from T, we know for sure that the shortest path from R to T in G is free from the failing edge. So the last edge of this replacement path was just added by the BFS tree that we added with respect to this node R, sampled node R. So this was the far fault. This is the easy case. Now for the near faults, it is very convenient to look at the following decomposition of the replacement path. So as we said it before, if this is in gray, you see the BFS tree. In black, you see the shortest path between S and T, and this is the failing edge E. We claim that the replacement path can be decomposed into 3 parts. We have the tree path, S to X. Then we have some linkage, X to Y. And then we have what we call the sensitive detour, the segment from Y to T that lies entirely inside the BFS tree, the subtree rooted at this edge. So all the edges, all the vertices along the sensitive detour are sensitive to the failing of the edge E because the edge E appears on the shortest path for all these nodes, okay? So we have a tree path, then a link edge, and then a sensitive detour, a detour that is sensitive to the failing edge. And the key observation is that for every 2 nodes A and B on the sensitive detour, it cannot be the case that their shortest path contains E. Okay, so this is just by a triangle inequality. Okay, so now we consider the near fault. I want to show that the algorithm actually adds the last edge PSTE for in the case where E is near. And there are 2 cases. The first case is where the sensitive detour, this part, is long, is at least sigma. In this case, with high probability, there is a sampled vertex R on this part, okay? And because we just say that 2 nodes on the sensitive detour, the failing edge E does not appear on their shortest path, again, this last edge of the path is already included in the BFS tree rooted at R. So this last edge is covered. The most interesting case is the second case where actually this sensitive detour is short. This is the only point where we are actually going to use the fact that we compute a truncated collection of BFS trees, okay? So here the key observation is that if the distance between E and T is at most sigma and the sensitive detour is of length at most sigma, it must hold that for every vertex W on the sensitive detour, the edge E is also close, is also near to this vertex W, okay? So if the edge E is near every vertex on this sensitive detour, it means that the BFS token propagates along the entire sensitive detour until eventually arriving T, and T will then add the last edge of PSTE. Okay, so finally, let me just mention some open ends. I mainly described here the multiple source case whose the sparsity of the output subgraph is optimal, but it's unclear if one can provide better around complexity. I would assume that yes. For the multiple sources, as we say in this paper, we just have subquadratic sparsity, sublinear round complexity, but it would be very interesting to sort it out and provide the best bounds, the best trade-off between the sparsity and the round complexity. And finally, the general case of F manifolds is still vaguely open. It would be very interesting to provide any meaningful result in this setting as well. So thanks a lot for your attention.